Hello, great welcome to this video on Eigenvalue Analysis using Seismostruct software. So as you can see, this is a main window for Seismostruct, and the software has three modules. One is here is a preprocessor wherein we input all the data required for the definition of the structure, and this is a processor area where after completing the preprocessor information we carry out the analysis, and post-processor is the module wherein we observe or we can obtain all the result analysis, including the deflector shapes, the various diagrams like the bending moment, shear force, the deflector shapes, mode shapes, etc. So here, as you can see on the left side, there's a button shows the different types of analysis. So for this presentation, we are selecting the eigenvalue analysis. So you can see the structure that is selected for the eigenvalue analysis. It's a simple steel structure, and it's a 2D analysis, and it's a steel frame that's of 25-meter height and 17-meter bay width. So as usual, we have to start with the materials. Here, as you can see, I have already defined an S275 material here with a yield strength of 275,000 kN per meter square, that is 275 MPa. And then here I have defined the various profiles for this steel structure, and you can see that all are European sections. That is, I have selected for columns HEA section. For the beams, I have selected the IP profiles. And then the definition of the element classes is a very important thing, and here you need to be very careful regarding the element type selections. So here for this analysis, I have selected the so-called inelastic force-based frame element for both the columns as well as the beams. For example, if you double-click this column, you can see this is the element. So you can see that the element class is defined by column CLS1, and we have already defined the element type here. And please remember that the Seismostruct can perform the complete analysis of the cross-section based on a fiber approach, wherein the entire cross-section will be divided into a number of fibers, each fiber being characterized by a stress-strain relationship. And from the equilibrium consideration, you can obtain all the behavior of this cross-section, and this is what we normally call as a fiber-based approach modeling. Okay, so here I have defined the element classes for the columns as well as the beams. Now below you can see I have also defined a mass element, that's an lumped element. For the mass element, there are two element classes available. One is a lumped mass and the other one is a distributed mass. Here please remember that for the eigenvalue analysis, the definition of the mass is very, very important. And here I have defined a lumped mass that is characterized by inertias, mass inertias in the three directions X, Y, Z. Here you can see that I have lumped 10.6 tons of mass in the X, Y, and Z directions, and I have defined damping in the project settings. And here one very important thing I want to mention, you go to, for example, here the project settings, please see here the gravity and mass. So the Seismostruct permits you to define the masses in three ways rather. One, directly you can obtain the mass from the frame elements, that's a specific weight and additional section mass and mass elements. And the second approach, you can directly obtain the masses from the loads applied. And the third approach, you can calculate the lumped masses both from the frames as well as from the mass elements. So you can select here, we have selected the first one, that is the frame element sulfate and the mass elements. So having defined the materials sections and element classes, we need to define the nodes that are required for the definition of the various element connectivity. So you can see that the nodes are defined by the XYZ coordinates, and there is also provision of defining whether a particular node is a structural one or a non-structural one. Okay, having defined all the nodes, you can go to the element connectivity, and for example, if you double click this column, which I have already defined, this column with an element name of column 821, and it is associated with an element class of a column CLS3 that is defined earlier, and it connects the nodes N721 and 821, and we have not applied any kind of a member release here. And we can also set the member orientation using this orientation facility available here. Okay, now if you see below, I have defined also the mass elements. For example, if you double click, here is a mass element name M1, and it comes under the element class mass CL, and that is lumped at the node N11. So having defined the nodes and the element connectivities, we can go to the constraint section. So this constraint section is a facility available wherein we can model the rigid frame action. For example, if I want to assume that the frame beams at the different levels are very rigid, I can make use of this facility. For example, here you can see that I have defined a master node. Okay, so for example, if you activate the nodes, so here is a show node labels, right? So here I have defined an N11, this is a master node, and all the other nodes at this levels, that is N121, N131, N141, they are slave nodes. Thereby a rigid diaphragm is created at different story levels. Then we have the constraints. That means we know that for any structure to analyze, we need to define the support conditions. So here I am going to define the support conditions, or the so-called boundary conditions associated with the base nodes N011, N021, N031, and N0411. Here I define all these nodes as fully fixed, as you can see here. That is X, Y, Z are totally restrained along with the corresponding rotations Rx, Ry, and Rz. So define the masses, nodes, all the structural details. We can straight away go for the processor. That means we can allow the program to run. So let us go run. Okay, fine. So you can see that it has given us the results so fast. So in order to see the mode shapes, the dominant frequencies, as well as the mass participation factors, let us go to the post processor. So here you can see that there is a very good facility available here. There's an animate 3D model. For example, let me just increase this. So you can see that the mode shape corresponding to the mode 1. So that is characterized by a period of 1.49. So these are deflected corresponding to the mode 1. So now similarly, let us see what about the mode 2. So you can see that the mode 2, and these are mode 3, these are mode 4. So these are the mode shapes. And now it is also very important for us to obtain what are the various result outputs provided by the program. So model mass quantities. Here you can see the output includes the mode number, the periods, the frequencies, that is the hertz as well as on the radian per second. And then we have got the very important factor known as a model participation factor. And here the program provides us the mass participation factors for different modes in the various directions. So let us go here down. So you can say here that the effective model mass participation, for example, for mode 1, we see that there is a 77.32 mass participation, and for mode 2, in the X direction, there is a 12%, and in mode 3, 4.89. So basically, as envisaged, this is a structure that is dominated by the first mode, and we can see that the mode 1 plus 2 plus 3 contributes to almost 90% of the total mass participation. So that's all, and please practice yourself, and all the very best.